Hi, my name is Vladimir Horikov, and this is the CQRS in Practice course. In this module, we will talk about synchronizing the commands and queries databases. We will also discuss eventual consistency and the CAP theorem in the context of CQRS. In the previous module, we introduced a new database for the read part of our application. This new database is perfectly aligned with the needs of our queries. It is denormalized and consists of only one table. The fact that there are now two separate databases means there should be a synchronization between them. Such a synchronization is also called projection. So keep in mind that the words synchronization and projection are synonyms in the context of CQRS. So let's talk about what strategies we could employ to implement such a projection. Those strategies can be divided into two categories by the type of triggers that drive them. First, it is the projection driven by state, and second, the projection driven by events. The projection driven by state, in turn, can be divided into two subcategories, synchronous and asynchronous. Let's take this first category, projections driven by state. It kinda sounds fancy, but it's really simple. The idea behind it is that you have a flag in each aggregates table that tells you the aggregate has been updated since the last synchronization, and you need to synchronize it once again. In our sample project, the command side of the application contains two aggregates, student and course. And so you wouldn't need to add 4 new columns, one per each table, but rather just two, one for the student table and the other one for the course table. You can call it isSyncRequired, isDirty, or something similar. So whenever a student gets updated, and that includes the data in the student, enrollment, and disenrollment tables, whenever they get updated, you raise the isSyncRequired flag in the student table. A separate synchronization process that runs at background then picks it up and either inserts a new row into the read database or updates an existing one. After that, it resets the flag. You can also add a separate small table named synchronization with another flag in it called isSyncRequired. This table will have just one row. Whenever any flag in the database is raised, the flag in that small table will be raised as well. The reason for this separate table is that the background synchronization process will be sampling changes in the commands database pretty often and may potentially put a lot of pressure on the student and the course tables. The additional table will allow you to offload that pressure. Now the synchronization process will be sampling just this one table instead of all students and courses. It will query the students and courses only if the flag in the synchronization table is set to true. This projection mechanism is very straightforward, simple, and also easy to use. If you would ever need to rebuild the read database, you just need to raise the flag for all records. And you can do that selectively too for just a subset of records. There are two ways to implement the commands part of this mechanism, the part that is responsible for raising the isSyncRequired flags. First, create a database trigger. This trigger would monitor changes in all of your database tables and updates the flags accordingly. For example, if we enroll Alice in a new course, a new enrollment row will be inserted. The trigger can interpret this insertion as an update of the corresponding student and can raise the flag for Alice's record, as well as the flag in the synchronization table to let the background synchronization process do its job. Note that in order to handle the deletion, you would need to modify the way you handle unregistering of students. Instead of actually deleting them, you would need to implement a soft deletion with the isDeleted flag. Then the deletion of a record will be treated the same way as a modification of it. There is a fully fledged example of this technique with state-driven asynchronous projections in my other course named Domain-Driven Design, working with legacy projects, in the module about synchronizing anti-corruption layer, so check it out for more details. The second way to raise a flag is to introduce it in the domain model itself explicitly, instead of relying on a database trigger. You can add two new isSyncRequired properties to the domain model, one in the student entity and the other one in the course one, and update those properties whenever the client code modifies anything in those aggregates. That's pretty easy to do if your domain model is encapsulated. Here's an example. You can see that when we remove an enrollment, we raise the isSyncRequired flag too. And of course, to make this work, you would need to override the setters of the name and the email properties so that whenever the client code assigns a new value to them, the flag is raised as well. To raise the flag in the separate synchronization table, you can use event listeners in Hibernate or the change tracker in Entity Framework. This way, whenever you see an entity is being persisted with the isSyncRequired flag, you will be able to automatically raise the flag in the synchronization table too. To see an example of it, refer to this article, section number 7. So which one of these two ways to raise the flag should you choose? The one with the trigger or the one with the flags in the domain model? If you have control over the domain model, then go the explicit route, with the explicit flags in the domain model. It's always better to be explicit about what you do in the code. It tremendously improves the maintainability of your codebase. Choose the approach with the database triggers only if you don't have other choice. For example, when you don't have control over the domain model. That was an example of an asynchronous state-driven projection strategy. The projection is driven by the state of the database, particularly the isSyncRequired flags in it. And there is a separate background process that does the actual projection. It monitors those flags and rebuilds the query database if it sees any changes. Let's now look at synchronous state-driven projection strategies. The difference between them, as you can guess from their names, is that one of them runs synchronously and the other one asynchronously. So what that means exactly? The word asynchronous means without blocking the main worker. In the examples we discussed previously, the application is able to update a student in the database and continue working. A separate process then picks up this modification and does the projection. Our application doesn't wait for that separate process to complete this job, and so we can say that the projection is done asynchronously. So how the synchronous version would look then? The synchronous version is when the application itself does all the work or waits until the background process completes the projection before returning an OK to the client. This approach is rarely applied when you have two separate databases for reads and writes, mainly because it increases the processing times quite dramatically. However, the benefit here is that the read and the write models are immediately consistent, which eliminates this confusion from the users when they don't see their changes immediately after submitting them. It might be very helpful if this is a strong requirement from your customer. I wouldn't recommend that you normally do that though, at least not when there are two separate databases for commands and queries. Either implement the projection asynchronously or keep the read and write models in the same database to decrease the latency. Because of the additional latency, the synchronous projections don't scale well. That's because the latency will increase each time you add a new database copy for the queries. Your main application will have to update all the read databases on its own each time it modifies anything in the commands database. And the more databases you introduce for the reads, the more time it takes your application to update them all. There are two common examples of the state-driven projection strategies. Indexed views is an example of a synchronous projection. That's because all indexed views in relational databases are updated immediately along with the tables they derive their data from. An example of an asynchronous projection is database replication. Database replicas, unlike the indexed views, are updated asynchronously. Another category of projections is event-driven projection. The main differentiating factor here is that event-driven projections are not driven by state, but instead they are driven by domain events. So instead of the isSyncRequired flags and instead of the separate synchronization table, the projection process will subscribe to the domain events the command side raises and will use the information from those events to update the read database. The benefit of this approach is that it scales really well, even better than the approach with asynchronous state-driven projections. That's because your application can just publish the domain events on a message bus and you can have as many projection processes subscribing to those events as you want. They will not put additional pressure on the commands database. However, there is a significant drawback to this approach. There is no easy way to rebuild the read database from scratch or rerun the projection in case of an error. In our commands database, the source of all data is the state, the current state of the students and the courses. We don't store the domain events that led to that state. And because it's impossible to derive the domain events from the latest state, your read databases will become out of sync should they miss any domain event for some reason. You could mitigate this issue by storing the domain events along with the state in the commands database, but that would be quite a significant complexity overhead. And really, if you're going to store the domain events in the database anyway, then you should probably transition to an event-sourced architecture. Event sourcing is outside the scope of this course, though. So the rule of thumb here is this. If you are implementing the CQRS pattern without event sourcing, that is, you don't store the domain events in your commands database and just persist the latest state instead, then don't employ the event-driven projection approach. The state-driven projections would be a much better fit for you. On the other hand, if you are using event sourcing, where the domain events are the first-class citizens in your database, then of course use the event-driven projections. In this case, you will be able to rebuild the read database by re-raising all the events in your commands database. In other words, align the projection strategies with the type of persistence mechanism you have chosen for your project. We discussed in the previous module that having two databases instead of one introduces latency between the write and the read models. It brings in a potential confusion for the users, and you should carefully consider this drawback. For example, after registering a student, the user might not see that new student immediately, decide that they did something wrong, register that student again, and end up with having two identical student records. If your customer strongly opposes such a user experience, then just go with a single database for reads and writes. You will still gain most of the benefits of the CQRS pattern. However, if your customer is not opposed to relaxing the consistency requirements, there are some ways to mitigate this potentially confusing experience. First of all, in many cases, there will be uniqueness constraints on most of the data in the commands database, and that will help avoid the duplicates. For example, there might be a requirement that all students' email addresses must be unique. In this case, even if the user doesn't see the new student right away and try to register them again, the system will return an error saying that such student is already registered. Note that the consistency issues only involve the queries database. The commands database is always immediately consistent. And because you run the uniqueness constraint validations against the command database, there will be no duplicates, and the user will receive a proper error message. Let's actually elaborate on this point. People often ask, what if I need to query the database during a command execution? For example, to check for the email uniqueness constraint. And should I run a query from a command handler to do that? And the answer is no. You shouldn't use a query for that because the queries work with their own database that might not be up to date with the commands database. In order to verify that the email is unique, you can query the data storage, but that should be the commands data storage because it's always up to date. Just use a regular repository or the unit-of-work class for that. So you will still need to read the database from your commands. The difference between such reads and what the queries do is that the reads the commands perform are part of the command processing flow. The results of those reads don't cross the boundaries of the application. In other words, they are not intended for the user. Remember, after finishing the full separation between commands and queries in the previous module, we still had some read operations remaining in the repositories. That's the read operations I'm talking about. Get student by ID, get course by name, and potentially get student by email. They are intended to serve the commands, not queries. Note that it's a different story if you're implementing event sourcing. In this case, you're not able to efficiently query the current state from the commands database, because your database stores events, not the state. And so you will need to query the read database in this case. You won't have any other choice. and you will have to deal with inconsistencies that flow from that. That's a whole other topic though, and it should be addressed in another course. We will not be diving into it here. Alright, so uniqueness validations are one way to mitigate the issues with the consistency. Another way to do that is to train your users not to expect the data they see on the screen to be immediately consistent. I know that sounds like cheating, and it looks like it just shifts the burden from lazy programmers to the users. After all, the software will become less usable if the users wouldn't see the results of their actions immediately, right? Actually, no. While it might be plausible to think that the users expect immediate consistency all the time, in reality, they don't. In fact, the whole concept of immediate consistency is counterintuitive because it's not how the things work in the real world. Think about it. When you move to a new home, do you expect your driver's license to reflect this change immediately? Of course not. Your driver's license will show the old address until you go to a DMV and ask them to issue a replacement. And during this quite long period of time, the information on your current driver's license will remain stale. It will remain obsolete. All your interactions with the real world are inherently asynchronous and involve eventual consistency. And the world around us is eventually consistent too. Heck, even physics itself is eventually consistent. The information in the universe is passed with the speed of light, which is quite fast, but it's still not instantaneous. And so it doesn't take your users much effort to learn the concept of eventual consistency, because they already experience it in the real world. And in fact, it's the concept of immediate consistency that they learn when they start working with computers, not the other way around. You have probably already understood what eventual consistency stands for, but let me give an official definition. Eventual consistency is a consistency model which guarantees that if no new updates are made to a given data item, eventually all accesses to that item will return the last updated value. So in our example with the commands and queries databases, it means that if we modify a student, this change will eventually propagate to the read database and our users will be able to see it on the UI. You can foster the user acceptance of the eventual consistency by displaying helpful messages and setting proper expectations. For example, when registering a student, show a text message saying that the student registration is submitted and will be processed shortly. This way, the user will understand that this process takes time and they shouldn't expect it to be completed immediately. Another way to handle this is to trick your users. Whenever they register a student, do update the student list, but do that locally, on the user machine only. By the time they refresh their screen again, the student will already be in the queries database, and the query result will contain the latest data. You can go even further and implement a two-way communication between the UI and the read model. So whenever the read model receives an update, it will send a message to the UI with the updated search results. That would add some complexity though, because you will need to keep the connection between the UI and the backend open. And in most cases, a simple message or the trick with the local data update would be enough. So to summarize, if you decide to introduce a separate database for reads, then your query site will not be immediately consistent. It will be eventually consistent, which might or might not be acceptable depending on the requirements your stakeholders pose to your application. There is a great article about how consistency is handled in the real world, called Starbucks Doesn't Use Two-Phase Commit. Check it out here. There could be one area where the eventual consistency is problematic, and that is when you need to make a decision based on the current data and the cost of making that decision based on the stale data is very high. This is almost never the case, though. One of the few exceptions here is high-frequency stock trading. In all other cases, you can mitigate this problem with versioning. You can keep a version of an aggregate in both the read and write databases, and then if you see that the user tries to update the stale record, show them an error. This is called optimistic concurrency control. Here's an example. Let's say that you are requesting a list of students from the read database, and it returns you Alice's record with version 1. Let's also say that someone updates Alice's personal information, and so the version of her record in the commands database becomes 2. Then you also try to update her personal information based on the stale data from the query's database. In order to mitigate this issue, you just need to make this version number part of all the communications between the UI, the command, and the read models. So when the UI queries the read model, it receives the version number and includes it in the command that it sends to the write model. The write model can compare the version number in the command with the current version number in the aggregate, and if they are different, it can raise a concurrency error and reject the change. This way, you will inform the user that they need to refresh their screen to see the latest updates and include them into the new update request. There is a closer relationship between CQRS and the CAP theorem. The CAP theorem states that it is impossible for a distributed data store to simultaneously provide more than 2 out of the following 3 guarantees: consistency, availability, and partition tolerance. Consistency means that every read receives the most recent write or an error. Availability, that every request receives a response, apart from outages that affect all nodes in the system. And partition tolerance, that the system continues to operate despite messages being dropped or delayed between the network nodes. For example, if you choose availability and consistency, that would be a typical relational database server running on a single node. All read requests to this server always get the latest version of the data, and this server is always available. The drawback here is that there is no partition tolerance, meaning that you cannot have more than one server working for your application. If you choose consistency and partition tolerance, that would be an anti-pattern called distributed monolith. All reads to such a system will still be fully consistent with the writes, but because you also chose partition tolerance, there are now multiple servers, and to ensure the consistency among all of them, you will need to block the whole system and wait until each change propagates to every server. This would make the system unresponsive and unavailable for the period of time during which it waits for the propagation to complete. Imagine what would happen if, when you post a picture on Facebook, the whole website would stop working to ensure that your friend's newsfeed is consistent with your latest update. And finally, if you choose availability and partition tolerance, then you do that at the expense of consistency. Which means that if there is a connectivity loss between 2 servers and you allow them to work independently, then they go out of sync with each other really quickly. So again, you can pick 2 out of the 3 guarantees, but you can never pick all 3, which means that you need to find a proper balance for your particular situation. CQRS is great because it allows you to make different choices for reads and writes. The trick here is to make the trade-off between partitioning and consistency differently on the read and write sides. In most cases, you can give full consistency on the command side and give up a level of partition tolerance. That's the typical relational database server scenario. You can do that as long as all your command handlers can operate on a single machine. At the same time, you can give up the full consistency on the queries side in order to obtain partitionability. You want to ensure partitionability on the read side because you want to scale the reads up to several machines to enable scalability. And you want to ensure consistency on the write side to make sure all changes are consistent, at the expense of having only one machine that handles the commands. In this module, we discussed the synchronization between the commands and queries databases. Such synchronization is also called projection. You learned about the 2 projection strategies, using state versus using events as drivers for it. State-driven projection is when you introduce an isSync_required flag in the aggregates tables and raise it whenever there is a change to them. You can use this flag using database triggers or explicitly in your domain model. The explicit route is the better choice in most cases. The state-driven projections can be synchronous and asynchronous. Synchronous projections don't scale well, so choose the synchronous option by default. We also discussed event-driven projections. That is when you use the domain events raised by the command side to build the queries database. The rule of thumb here is this. If you are implementing the CQRS pattern without event sourcing, That is, if you persist the state, then use the state-driven projection. If you persist events instead of state, then choose the event-driven one. We talked about immediate and eventual consistency. Although you might be used to immediate consistency in the world of relational databases, that's not how the real world operates. And people usually don't have trouble dealing with eventual consistency in the software too. Just set proper expectations and implement data versioning to enable the optimistic concurrency control. Finally, we discussed the CAP theorem in the context of CQRS. Remember, CQRS is about making different choices for different situations, particularly for read and write sides of your application. And that is also true when it comes to finding the balance within the CAP theorem. Choose consistency and availability at the expense of partitioning for writes, and choose availability and partitioning at the expense of consistency for reads. In the next module, we will talk about CQRS best practices and common misconceptions.